Okay, next we have the internal energy of an ideal gas. First we will define the internal energy. What is internal energy? It is that basically the translational energy, sorry, or the translational kinetic energy associated with the molecules of an ideal gas. Is known as internal energy. Of an ideal gas. So internal energy basically means the translational kinetic energy. So the translation kinetic energy is basically called the internal energy of an ideal gas. Now we know that the translational kinetic energy, or we can say that the translational kinetic energy is related to the temperature by this relation. We have the translation kinetic energy, which is 1/2 mv square. This is the average value or the mean value of energy. Okay, so it is the translation kinetic energy which is related to the temperature by this relation 3/2 kT. So this is a well-known relation, and we already proved it in the previous videos. Now here we know that this 3 is constant, 2 is constant, and this k is basically the Boltzmann constant. It is called Boltzmann constant. So it means that this translation kinetic energy, half mv square, is equal to some constant. The constant are 3/2 k, some constant times this t. Now if I remove this constant, what it means? It means that the translational kinetic energy is proportional to the temperature. So the translational kinetic energy here is proportional to the temperature. Now, so we can say that the internal energy, E internal, INT here in the subscript represent the internal, and E means the energy. So the internal energy is basically equal to the translational kinetic energy of the molecule. Now let's say this is my equation number 1 and this is my equation number 2. Now we know that if n is the number of moles and if m is the capital M, represent the molar mass, and the small m represent the total mass of all the molecules. Then we have a relation which is given by this. N is equal to m over m. It means the number of moles is basically equals to the total mass divided by the molar mass. From this I can get the total mass, which is m, which is equal to n times molar mass. Number of moles times molar mass. So this is, let's say, my equation number 3. Now if I put equation 3 into, so using equation 3 into, we have, if I put the value of m from equation 3 here in equation 2, I replace this m in equation 2 by this relation, then we have this internal energy, which is E internal, which is equal to, now here we have this 102 and m, they are both constant, so I can keep it from this average value. So we have 102 m into v square. Now instead of m, now I will put 102 nm into v square. I can say that internal energy is equal to 102 times, this is the total mass, into v square, and this is the mean square velocity. Now we know that total mass is basically, we know that density is basically equal to mass per unit volume. So the total mass will be equal to density times volume, because from this we can get mass is equal to rho into v, where rho is the volume density and v is the volume. So the total mass is equal to density times volume, rho into. So if I put this value in above equation, then the expression for the internal energy will be 1 over 2 rho v, where v is the volume, okay, this capital V represent the volume, and this v basically represent the velocity. So it is the root mean, mean square velocity. So this represent the mean, and here we have the square, so it is the mean square velocity. I can write this in this form: E internal, or the internal energy, which is equal to 1 over 2 rho into v. This capital V represent the volume, and this small v represent the velocity. Let's say this is my equation number 4. But we also know that for ideal gas, the pressure is related to the volume, the pressure is related to the velocity by this relation, 1 over 3 rho into v square, where this v square with this sign represent the mean square velocity. We already proved this relation, okay. So it means that the density, if I calculate the value of density from this relation, then it will be equal to 3p over v square mean. Let's say this is equation number 5. Now here I will put this equation 5 and 4. So using equation 5 and 4 we have, so equation 4 is E internal, or the internal energy, which is equal to 1 over 2. Now we have this density, so instead of density I will put 3p. I'll put 3p over v square mean, and we have this volume, and then we have v square mean, or the mean square velocity. So the mean square velocity cancel with this one, so we have the internal energy which is equal to 3 over 2 PV. But we know that PV is equal to nRT, so the internal energy is equal to 3 over 2. So I'll replace this PV by this relation nRT. This is one form of the internal energy. So we know the internal energy is basically average translation energy, kinetic energy, which is 1 over 2 mv square. One relation for the internal energy was this one, and we have another relation which is given by this one. So this implies that this equation shows that internal energy only depends on what? Temperature. And it is independent of pressure, volume, etc. So internal energy, E internal, is the internal energy depends on temperature and is independent of pressure, volume, etc. Now we also know that, so this is, let's say, equation number 6, okay. Now we also know that we have this relation, which is the number of moles is equal to N over Na, and we have another relation which is R is equal to K into Na, where Na is the Avogadro number. So using these values, like this value and this value, I can say that using these values in equation 6, equation 6 is this one, internal energy which is equal to 3 over 2 and we have this small n, so I replace this n by this n over Na, and we have this R, so I replace R by K into Na, and we have this T, so Na cancel with this Na, so we have the internal energy which is equal to 3 over 2, we have Nk into T, and this is equation number 7. This is another form of internal energy. Again here internal energy depends only on temperature, because 3, 2, N and K, they are all constants. So internal energy depends only on temperature and is independent of pressure and volume. Now we derive this equation by assuming the molecule of a gas is a single particle. We consider a container, and we suppose that this container is filled with a gas, and these are the molecules of the gas. So we consider each molecule as a single particle. This is a molecule, and we assume it is a single particle. Single particle. Now, this single particle, if it is a single particle, then there are three possible motion of this particle. It either move, if this is my x-axis, this is my y-axis, and this is z-axis, then this particle, this is a particle, this particle either move in x-axis, or it's either move in y-axis, or it's move in z-axis. So there are three available path for the motion of this particle. So this point particle has three independent this point particle has three independent paths for motion. And these three independent paths are basically called degrees of freedom. Degree of freedom. So it means that this point particle has three independent paths for the motion, or we can say that this point particle has 3 degrees of freedom. So what is a degree of freedom? Here I will first define the degrees of freedom. Degree of freedom. It is basically the number of direction in which a molecule may translate or the molecule may rotate or the molecule may vibrate is known as degree of freedom. So I will stop my video here, and the next video I'll proceed further from this point.